Hey, I will do screencast of the next Vertices second division round. I think this time I will refrain from drawing anything using my graphic tablet because the last time I tried to do so was in last Coder regular contest, which I was also trying to do screencast as commentary on, and like half an hour into the competition everything froze, and so screencast was lost, and I had to hard reboot my laptop. So for now let's stick to voice explanations. I hope it will be understandable somewhat. In problem A, we are given some number x, which is at least 2, and we have to find two numbers such that their GCD plus their LCM is x. Well, let's find numbers that their GCD is 1 and their LCM is x minus 1. To do this, we can take like numbers 1 and x minus 1. And that's all. This is a nice problem. So we have an array of integers of length n. Then we copy it n times. So we now have array of length n square, and we ask to find the length of its longest increasing subsequence. The important part is that the length of initial array and the number of times we copy is the same. If it wouldn't be true, then this problem will be at least as hard as like just find the longest increasing subsequence, because for example we could copy array one time, and well, maybe it's even harder than that. But since we copy n times, we can see that the length of longest increasing subsequence cannot be more than the number of different elements, because well, obviously in subsequence, in increasing subsequence, all the elements should be different and they all should be from our initial sequence. So the number of the length of longest increasing subsequence cannot be more than number of different elements, but we can also achieve that just by like taking the smallest element in first copy, the second smallest in second copy, the third smallest in third copy, and so on. The number of copies is n, so we won't run out of copies to take elements from, so the answer is just a number of different elements. For counting number of different elements, let's use std set. Just will place all the elements in set, and its size is the number of different elements. Okay, we are given a tree. We have to write some permutation of numbers from 0 to n minus 2 on its edges, such that then we will take every pass in this tree, a pass between some two vertices, calculate max of number of edges on this pass, where max is the minimal number that is not in this set, and we want this number to be as small as possible. Well, basically the answer is if we want our max to be at least k, max of some pass to be at least k, we have to get all the numbers from 0, 1 up to k minus 1 on this pass. Otherwise the max will be some number smaller than k. So I state that either the tree is bamboo, and then we could just take the ends of this bamboo, and all the numbers between 0 and n minus 1, n minus 2 will be on this pass, so the answer will be n minus 1. And otherwise there is a vertex with degree at least 3, and we can write 0, 1 and 2 on 3 edges from this vertex, and then the answer is 2, because no pass can contain all these 3 edges. We cannot get less than 2, only if n is equal to 2, because for every 2 edges there is a pass that contains both of them. So to solve this problem, you could just find the vertex with degree at least 3. If there is at least 1, then we will start writing numbers starting from this vertex, and the answer is 2. And if there is no such vertex, then we can do nothing, so every permutation will be okay. will have array ans for all edges. We will initialize it with -1s, so the answer is yet to be decided. Well, why I do this? Now I will read the edges, and for each vertex I will store the IDs of edges incident to this vertex. Then I will go through the vertices. And if the vertex has a degree at least 3, then I will set the numbers starting from 0 from this vertex, like to edges going out of this vertex. You can see that I can find more than one vertex. It's okay. The important part is that when we find the first vertex, we will start from 0 and go at least up to 2, and everything after that is not important. Okay, this is not great. Okay, so we have two numbers. We have to construct the shortest array such that XOR of elements of this array is the first number and the sum of elements is the second number. Well, obviously XOR is not greater than sum. If it is in this case, then it's impossible. If they're equal, then we can have array of length 1. If the sum is 0, then we have empty array. Yeah, if they are equal, then the answer is 1. I wanted to say that in all other cases we can construct array of length 2, but looks like it's not true. Let me think, why is that? What else can we say? The parity of these two numbers also should be the same, otherwise it's impossible, because the parity of XOR and sum calculated in the same way, so they should be equal. Um, Obviously, the length of answer is not greater than 3 because we can always get 3 by taking the array u and v minus u divided by 2 twice. The XOR is 0, so the XOR of whole array will be u and the sum will be v because we have chosen the numbers to satisfy. And I guess we should somehow determine if it is possible to do in two operation in array of length 2. Well, what is the difference between XOR and sum? When we do XOR, we don't do we do operations bitwise, and if we have both ones, then we don't add to the next we don't carry a 1 to the left, and when we do summation we do. So basically we can say that sum is XOR plus AND multiplied by 2. So if we have two numbers, then we know their XOR, we know their AND. So when we calculate AND, we know that in those bits that have 1 in AND, there should be ones in both numbers, and the bits that have 1 in XOR, they should have 1 in exactly one of numbers. So if they have like intersecting bits, then it's impossible. Otherwise it's possible, and we can just take XOR plus AND, and the second number will be just AND, the XOR will be U, and their sum will be V. Okay, I think that I have seen these problems. For sure I have seen a problem about like given XOR and sum of two numbers, find these two numbers. So this is just some variation, and like it's not great. It doesn't add much. I think maybe this exact problem was used sometime before. So if XOR greater than sum, then it's impossible. If they have different parities, then it's impossible. If the sum is 0, then XOR is also 0 because they have equal parity, or because XOR should be not greater than S. If they're equal, then you can just print X or S. They're equal after all. Their AND is S minus X divided by 2 if there are two of them, and if A and X equal to 0, then two numbers are enough. So in problem E, we have an array of numbers up to 10 to the 6. We have to find the shortest non-empty subsequence such that the product of the numbers in this subsequence is a perfect square, that is a square of some integer, and we have some special condition such that every number in this sequence has at most 7 divisors. Well, when you see a problem with some special condition on input, first you should understand what this special condition is. And in this case, well, suppose some number is a product of some prime powers, then the number of divisors can be calculated like this. So the number x is p1 in power a1 times p2 in power a2 and so on. So its number of divisors is a1 plus 1 times a2 plus 1 times a3 plus 1 times so on. Why is that? Well, because to get a divisor we can use only these prime numbers, and we should get some power that is not greater than ai. So to choose power for this prime, we have a1 plus 1 possible options like 0, 1 and so on up to a1, and that's true for all primes, and they're totally independent. So we know that this thing should be at most 7. We know that every such bracket is at least 2, because we care only about primes that we really have. So if we have at least 3 such brackets, then it will be 2 times 2 times 2, 8, which is already greater than 7, so we can't have this. So our number is either 1 or some prime power where a is up to 6, because a plus 1 should be at most 7, or it can be product of 2 different primes, or maybe one prime is in square and the other one is not. Well, what's next? Now we have to think about product being perfect square. Well, that actually means that when we take a product of some numbers, we independently sum up the powers for each prime. So when we choose some numbers, we will sum up powers for each prime. What does it mean to be a square in this sense? Well, each this power should be even. So actually we just we care only about parity of the powers, and all primes are independent. Well, they're not independent in the sense that we cannot take only some primes from a number, but in a sense, in multiplication or being a perfect square, all primes are independent. So we actually care about only about what primes do we have in odd powers? Like basically we take all the powers modulo 2, so the ones that we have in even powers, they are like non-existent. So we actually care about only do we have them in odd power, and we can see that like maybe we have this p in odd power, here we have p and q in odd power, and here we have only q in odd power. The thing is we can't have more than 2 primes in odd powers, and this really makes this a problem about graphs, I think. Let's make a graph. We will have a vertex for each prime. So we have some numbers that don't have odd powers, then we can just take them as is, and we will have a sequence of length 1, which is great. We have some numbers that only have 1 odd power, then it just it corresponds to having this prime. If we have 2 such numbers with equal primes, we can just take them, and their product will be perfect square. And if we have 2 different primes with odd powers, we will draw an edge in our graph, and basically we want either a path between two primes for which we have numbers that only have this one prime in odd power, or we want a cycle in this graph. We don't even have to restore the answer. Okay. So the numbers are up to 10 to the 6. I think that that is for 2 purposes. First purpose is that we have to be able to factorize the numbers, and for this we will use Vertices sieve with pre-calculated minimum prime divisor for each number, so we can factorize in the sum of these powers, which is logarithm always, and in our case it's when like O of 1 bounded by 7 for sure. And the second reason is that well, we have to have not many different primes, but it's like n times something small, so it wouldn't care if it will be bigger, but well, as I said before, we have 2 parts. Two parts in our solution. Well, we have zeros part, which is like factorizing numbers, finding if they're perfect squares already, etc. Like there are 2 ways to construct a good sequence. It is either a chain which has on both ends primes for which we have numbers that only z prime is odd, And the second is cycle. Finding the shortest cycle is like not the easiest problem, as far as I understand, but like we know that we have edges only in this case, so it is a product of two primes. And well, like one of these primes should be always less than 1000, and the other may be not, and they can be used in cycles. Interesting. Well, at least we can say that at least one of the primes on our cycle will be or at most 1000. There are like 200 such primes. We can try all of them. Then how to find cycle, like the shortest cycle containing this one vertex? Well, we will delete this vertex and run BFS from all the vertices that were neighbors to one we deleted, and we will remember for each vertex from what vertex we will find the shortest distance, and then we will go through all the edges, and if the edge is between two vertices that has two different like roots in their BFS tree, then we find a cycle, and like one of the for shortest cycle we will surely find it. So that should work in n times the number of primes, which is 200, which is okay. Let's go. we also should discuss how to find the shortest chain between two good vertices. Well, it's done in the same way. We will run BFS simultaneously from all these vertices. For every vertex we will remember the root, and then we will try all the edges which will connect the two trees and choose the shortest of them. So now I calculated the minimal prime power for each number. It will be more convenient to renumerate all the primes from 0 to n and use its label and not the number itself. Well, we could use the number to calculate the label for it. It's also not hard. It will be the vector of all the primes that appear odd number of times. Now I have to factorize the number. And if it appeared odd number of times, then I will push it here, not x but id. That shouldn't happen. Either we have 0, 1 or 2 primes that have odd powers. If we have 0, then we could just take this number, it is a perfect square, so ans equal to 1. Otherwise we have some numbers that have only this prime, and in this case we have to add the edge between these two primes. If we have some primes that appears 2 times, at least 2 times, then the answer is 2, and we can just print it because the answer is not 1. We don't have perfect squares. And now we have 2 parts. So the first part is to return BFS from all the primes that has at least one well, exactly one. If it has two, then the answer is two. From all the places that has a number for which only this prime has odd power. Well, okay, I will yeah, sure, that will work. So then I do BFS, and I will relax the answer inside BFS. It should work okay for both the first and second part, because they have the same constant we should add. Now I want to find the cycle. I should start the search only for primes that are smaller than square root of c. It can happen that we have parallel edges. In that case, I can take these two numbers and the product is perfect square, so I should update the answer with 2. So if it is not n, then answer well, it cannot be less than 2, but okay. And otherwise I should put it in the queue as a possible root. Oh, and I should also ban like vertex AD. Okay, I will put it in BFS. Like I only have to ban one vertex or 0, so I can just give the function the ID of vertex that I have to ban. in this case we haven't been to this vertex, and we should. The root is the same, and put it in the queue. This one. And in this case we have an edge that connects to vertices that have different roots, and we have to update the answer with the distances to them plus 3. Why is 3? Well, in the first case, when we find the path, like one from the edge I'm traversing right now, and one for each number on the end of a chain. And for the cycle case, it's 2 edges from the vertices I have deleted, and plus 1 for the edge I'm traversing now, and I have to bend this, check if it is bent. That's all. I have BQ for some reason. Okay. Oh yeah. minus 1. Oh, I'm numbering. Okay. I should number vertices from 1. Well, I don't like this. So I used 0 as a default value and also 0 as a ID of 2. That's a stupid mistake. Now it's not working. Oh, minus 1 here. And also here. So yeah, in problem F, we have undirected graph, and it's the one of the types of problems I like, and I even set one. So we have two hard things, like maybe NP hard, I think so. So we are asked to find independent set of size at least square root of n, or a cycle of length at least square root of n. It's hard to do one of these things, but maybe it's not hard to do one of them. Well, for example, if there was one example of such problem is to either like color a graph in k colors, or find a path of length k. Both of them are in NP hard, but to do one of them, we could just do a depth first search from any vertex, and if the height of the tree we have is at most k, then we can color in k colors just by assigning the color like the height of the vertex, or we have find long path. So probably we have to do something similar here. Or maybe like the less constructive way is to use some greedy to find one of things, and if that failed, maybe we found another thing. let's do DFS from some vertex. We will get DFS tree. Like the most important thing you have to know about DFS tree is that all the edges that are not in this tree are vertical. They connect two vertices that one of them are ancestor of another. And if we have an edge that is not in tree and it connects two vertices on like that difference of their heights is at least square root of n, then we have our cycle. And this edge and pass in tree. Otherwise, we know that no edges are connect vertices that are on distances square root of n and more. So we can like my first idea was to take just some layer of equal heights, like fix some height and take all the vertices with this height. There are no edges in this set, obviously, because we can't have two vertices such as one is an ancestor of other and they have equal heights. But this set can be small. But now we can take not one such set, but like, let's take all the vertices that have some fixed remainder of height modulo square root of n. We have to choose constants properly, but this should work in general. I state that all of the sets are independent because like one layer is okay, and there cannot be edge between layers because because we would find the cycle. And we have divided all the vertices in square root of n groups. Every one of them is an independent set, so we will find an independent set that is of size at least square root of n. For convenience, I will calculate this k, which is bound answer. So now k is square root of n rounded up. So yeah, I said that we have to choose the constants accurately. Well, we want to find a cycle of length at least k. It means that if the difference in heights will be k minus 1, it is fine. So difference of heights, we want k minus 1 or more. So I check that it is my, well, it can be either my ancestor or one of the I don't know the right word. Well, backwards ancestor. So I check that its height is smaller than mine, and actually it is not my parent, because otherwise I'm just looking at the upwards and edge in the tree, and the difference of heights is at least what we need. Well, n is at least 5, so k is at least 3, and we should be fine, but whatever. So yeah, if we have found such an edge, then we have found the cycle. So I have to print 2, then the length of the cycle, which is h of v minus h of u plus 1, and then the vertices. If we didn't find the cycle, then we will find our independent set. And what do we know? We know that for each for all edges that are not in tree, this difference is strictly smaller than k minus 1. So if we will group by remainders modulo k minus 1, we will be fine. And that's important. If we would group by remainders modulo k, then we will have k groups, and k can be bigger than square root of n, and it won't do the trick. it says that we have found the cycle and it's the correct order. And we have also found the cycle. And yeah, that's the correct order again. And we have found some independent set. Cool. That's a nice problem, but it's not hard enough to be F, I think. I think yeah, E is actually harder. And we have 50 minutes to spare, I guess. Cool. Thanks for watching.